Welcome to our second lesson of the Grade 12 Geography CAP series. I'd like to thank you for tuning in. If you are a returning subscriber and if you are new, I'm Andrew Commander and I make videos on the CAPS curriculum. Now, in the previous video, we talked about or went through the concepts of atmospheric pressure, warm air, cold air, how that relates to atmospheric pressure, and how all of that relates to weather patterns. Okay, so if you haven't access to that video, please do, because you will be left behind. Okay, so it should appear on the top hand right of your screen, and we'll leave it in the description box as well. Okay, now let's revisit our CAPS document. So this guides us. This is a document that guides us on what we should be doing, and of course a sequence is organized. So this is our term 1, and the very first topic that your teacher will go through is mid-latitude cyclones. Okay, so mid-latitude cyclones, this is the first topic that you should be going through. Okay, so if you're studying towards the exams, please start here. Okay, as of course things build on from this, right? Now in the previous video, guys, we looked at the difference between cyclones and anticyclones. Okay, so we said cyclones, these are low pressure systems in which of course you have rising air. Okay, said that these are associated with, of course, when air rises up, which is warm air, okay, which would usually happen during summer or during warm days. Okay, so you would have warm air rising up, leaving an area of low pressure which would develop. So we said that this would eventually lead to condensation occurring, unstable weather. Okay, so it is associated with rainfall, cloud formation. Okay, so if you haven't again checked that out, you should do so, okay, before you access this video, okay, because I think it is really helpful. Okay, now so in this video we'll look at the general characteristics of mid-latitude cyclones, the areas where they form, okay, conditions necessary for their formation, and lastly stages of development and the related weather conditions. The reason why I won't be able to go through the last two is, for the sake of this video, I don't want it to be too long, because I really want to explain these, go through some of these in a detailed manner. And so I will be doing so. The next video should include the last two under the mid-latitude cyclones. Okay, all right, let's get into it, guys. Let's not waste any time. Now, a mid-latitude cyclone, let's break this word down, right? A cyclone, as we said, guys, is a low pressure system in which, of course, there is warm air rising up. Okay. Now, when we define it, okay, so this section, or this part of this concept refers to where we find it. This part of the concept, this part of the word actually refers to the type of aerodynamics that we expect, that you will find the type of weather as well. So if you watch again the previous video, the previous lesson, you should have a bit of an understanding of what we mean when we are referring to a cyclone. Okay, now we define it as a low pressure system that affects areas between 40 to 60 degrees north or south of the equator. Okay, now the 40 to 60 degrees north or south of the equator part directly points to this part, the mid latitude part. Okay, so mid latitudes are between 30 and 60, but in this case between 40 and 60, because at the 30-degree latitude it's actually a high pressure belt, which actually does it, which contrasts with cyclone, because cyclones do not or have their circulation disturbed when they encounter a high pressure belt. Okay, so looking at this, I'm sure you guys do know that we use 30-degree increments. Okay, so this is our 0-degree latitude. So latitudes, of course, are these horizontal lines that run, of course, from the west to the east. Okay, so we know that at 0 degrees is the equator, right? And we use 30-degree latitudes. Okay, so this is 0. So when I'm going up, okay, or to the north, right? So the northern half, okay, so the northern half of this globe is what we call the north or the northern hemisphere, right? And then the southern part or the southern half is what we call the southern hemisphere, right? So we use 30-degree increments. So this should be from 0 going up, it's 30-degree to the north, right? So 30-degree latitude north. Then 60-degree latitude north, and then of course the highest latitude in the north should be, or the biggest latitude should be 90 degrees north. Okay, so that means that we are actually going up in latitude, in terms of latitude, so from 0 to 90. So that's going from the smallest to, of course, the biggest latitude in the northern hemisphere, right? Do the same going south, right? So this should be again our 30-degree latitude south, 60-degree latitude south, and 90-degree latitude south, right? Again, this 0 is our smallest latitude, and going down we're heading towards our biggest latitude. Okay, so this is our biggest latitude in the southern hemisphere, the 90 degrees south, and this is our smallest latitude in the southern hemisphere. The same applies in the northern hemisphere. The 90-degree latitude north is our biggest, and 0 degrees is our smallest. Okay, so when we actually referring to mid, so mid latitude actually refers to, means middle latitude. So if this is the highest and this is the smallest, so if 90 degrees is the highest and 0 degrees is the smallest, so in between that, so in the middle latitudes should be between 40 and 60-degree latitude. Okay, so it should be in that particular region in the northern hemisphere, okay, and should be in this particular region in the southern hemisphere. So it affects these particular regions. Okay, we did not say that it develops here, but we are saying that this is the areas that it affects. Okay, so after development, this is where it moves into these regions between 40 and 60-degree latitude, northern hemisphere and in the southern hemisphere. Okay, so let's take a look at other information that describes mid-latitude cyclones. So we said that these low pressure systems actually affect these areas and these regions, and they have a clockwise rotation of air in the southern hemisphere. Okay, so inside this system, if you're looking at the top view of this mid-latitude cyclone, you should see air rotating clockwise. Okay, in the southern hemisphere. Okay, so because we are already in the southern hemisphere, I think you should memorize only this, and because in the northern hemisphere it's actually the opposite. So as long as you memorize the southern hemisphere, you should always know the northern hemisphere rotation is anti-clockwise. So saying that this cyclone or this low pressure system which affects these regions has a clockwise rotation of air in the southern hemisphere and an anti-clockwise rotation of air in the northern hemisphere. Okay, so again, as long as you remember this clockwise rotation that we see in the southern hemisphere, the rotation in the northern hemisphere should be the opposite. Okay, let's look at the area of development. Okay, so we're saying that these are located in the middle or temperate latitude. So these are the latitudes that I was referring to, the 30 to 60. Okay, but again, guys, we're strict on that. We are actually accepting 40 to 60 because at 30 we have, of course, a high pressure belt there, which of course contrasts or would not allow these cyclones to actually be at their best, or actually would disrupt this circulation. Okay, um, and then between so they are between latitudes 40 to 60, okay, degrees north and south of the equator. This forms at the polar front, okay, where warm westerlies and cold polar easterlies meet. Now let's talk about the types of winds that we have, the major winds that we have, right? So due to differential heating, so differential heating is basically simply the fact that the sun heats up Earth differently. Okay, so this is the sun and this is Earth right here. So because the equator is situated at the center, the sun's rays are concentrated at the center. Okay, so they are spread like that, but right at the center, right at the equator, we have more concentration of the sun's rays. Okay, and so that means that the equator becomes very hot. So the equator is relatively hotter than the rest of the other areas, the rest of Earth. Okay, so that's why you'd find that the poles are actually colder, because the sun's rays, they actually hit these poles at an oblique angle. So whereas the sun's rays hit the equator at they hit it directly. Okay, so that's why the equator is actually hotter a lot than the other areas. So if an area receives a lot of sun rays, receives a lot of sunlight, what do we think about the type of air pressure that, of course, the air puts on the floor or on the ground? So let's think about this, guys. So you have, sorry about that, you have the sun and it's hitting a lot. So it's hitting the ground a lot. And so the ground then does what? It transfers this heat energy to the surrounding air particles. Okay, so the surrounding air particles become hot and they actually transform that heat energy into what we call kinetic energy. Okay, so this is the movement energy. So now they're excited. Okay, so air now will start to do what? Air will start to rise. Okay, so air now is rising because it has converted that heat energy into kinetic energy, right? So it starts to rise, and now let's think about the amount of atmospheric pressure or air pressure or pressure that this warm air puts on the ground. It actually puts a little pressure because remember, pressure, so guys, we said that it is really dependent on, of course, on the force and, of course, the size of the surface area. So the force that it puts on the surface is little, and hence the amount of pressure that it actually puts on the ground is little as well. So that's why that we say that warm air is actually associated or actually leads to an area of low pressure developing on the surface. So an area of low pressure will develop on the surface, and hence at the equator we actually find a low pressure belt there. There's a low pressure belt, guys, there. Let me actually use red. Okay, so I'll use red there. So that's why we see a low pressure belt there because of the differential heating, because the sun's rays are concentrated at this region, right? And so air actually rises up and so leaves an area of low pressure on the ground. Now, the surrounding areas are relatively high pressure areas. So, for an example, the 30-degree latitude, that's a high pressure belt there. Okay, so they are relatively high pressure belt, high pressures that you will find there. Okay, so that's what we are saying here. You find a 30-degree latitude, there's a high pressure belt, and because we said that um, air actually always will move from an area of high pressure to an area of low pressure, right? So air, that's the basic principle of air movement. So it always moves from an area of high pressure towards an area of low pressure. Now, is it going to move? How is it going to move? Is it going to move straight like this? Okay. Or is it going to, so it could move like that, but because of a force that we call Coriolis force, okay, which deflects wind, so it changes the wind direction. So instead of this wind moving from this high pressure belt towards this low pressure belt in a straight line, it actually deflects it to the left like that. Okay, so now you have, excuse me, now you have air that is actually being deflected in this manner. So it is deflected in this manner. Okay, so air is deflected in that manner like that. Okay? So this is the direction in which it deflects air, the Coriolis force, right? And this is warm air, right? Relatively warm air. Okay, and then so as you can see, guys, this is actually deflected towards the west, but we the way we describe wind direction, we describe it from as we look at where it comes from. Okay, is it coming from the west or is it coming from the east? Not where it's going to, right? So if you look at these arrows here, you can definitely see that you would say that this is actually coming from the east. Okay, and hence we call these easterlies. So we call these easterlies. Okay, and these are not the only easterlies, because this is the air from between 0 and 30 is also deflected, okay, like that. Okay, so that's how you have these easterlies. Okay, they are being deflected by the Coriolis force. So these are major winds. We call them tropical easterlies. So these, of course, are between 0 and 30 degrees. Okay, so they're between 0 and 30 degrees north or south of the equator. Okay, so we call them tropical easterlies, north or south, right? So these are called tropical easterlies, right? Now, at 60 degrees, we have a relatively lower pressure, okay, because of air that is actually being forced to rise up. Okay, now there's two ways that a low pressure develops. It's either warm air rises up because it has, of course, kinetic energy, or warm air is forced to rise up because it has encountered cold air. So if you have cold air and warm air moving toward each other, warm air will be forced to rise up because it is less dense. Okay, so it rises up, and then on the ground, because you have more warm air rising up, then on the ground you end up developing a low pressure, okay, or an area of low pressure, and that ends up developing. Okay, so that's another way that you can actually develop an area of low pressure. So that's what happens at 60-degree latitude. Okay, so the 60-degree latitude is also what we call the polar front, guys. Okay, the polar front. That's where you will find it. So I will talk a lot about the polar front when it comes to the development of mid-latitude cyclones. So that's what we call the polar front. So now you have again you have high pressure belt and a low pressure belt. Okay. So of course air, we said that always move from a high pressure belt towards a low pressure belt. So now air, of course, will want to move from the high pressure belt towards this, right? But it doesn't move in a straight line. But of course it's being deflected to its left like that. So it's being deflected like that. Okay. There we go. In the southern hemisphere, it's being deflected to its left in the southern hemisphere and to its right in the northern hemisphere. That's how it works. Okay. Now to its right in the northern hemisphere, so that means that it should be deflected like that. Okay. There we go. So what would you call these then? What would you call this type of major wind that is between 30 and 60 degrees north or south of the equator? You would call it the westerlies, okay, because they are coming from the west. Yeah, so call them subtropical westerlies, um, and these are relatively warm actually. So they would call it warm subtropical westerlies. Okay, so again, these are subtropical westerlies. Okay, between 30 and 60 degrees latitude north or south of the equator. Okay. Now I need you to note these, guys, because these will help you understand a lot. Okay, so you have to be able to draw this from, excuse me, from the start. Okay, and then at 90 degrees, because it is cold, you have a high pressure belt there. Okay, so high pressure belt. Yes, I'm just going to do that. So you have again a high pressure and a low pressure, and so of course wind will want to move towards from high pressure towards the low pressure. Okay, and of course in the southern hemisphere it will be deflected to the left, to its left. Okay, so there we go, deflected to its left like that, right? And these of course they are coming from the polar from the poles, and hence they are very cold. So these are cold polar what easterlies, right? Because they are coming from the east. So cold polar easterlies, right? Okay. Of course, that applies, of course, in the northern hemisphere as well. Okay. So now let's talk about where this forms. Okay. So we're saying that the mid-latitude cyclones actually affects we said that it affects these areas between 30, actually between 40 and 60, right? It affects these areas, but we did not talk about where it originates. Where does it form? Okay, because it only affects them, it does not form there. Okay, so it actually forms right here at the polar front. Okay, so it forms at the polar front. After forming there, it then does what? It moves into this region, okay, and affects all of these areas like that. Okay, so I need you to remember that. Okay, it forms here and then it affects, it moves into this 40 to 60 degree latitude and affects those areas, right? So let's look at where it actually forms. So we're saying that it forms at the polar front, which we said 60 it's at 60 degree north or south of the equator. And if you really look at this, you would actually find out that this polar front is actually between two major winds. It's between the warm subtropical westerlies, okay, and the cold polar easterlies, right? So you have two major winds with different densities, with different characteristics meeting up at this polar front, which is at 60 degrees. That's where it starts. So that's where mid-latitude cyclone originates. Okay, when you have this warm subtropical westerlies meeting up with this cold polar easterlies, that's where everything begins. Okay, when it comes to mid-latitude cyclones. So this agrees with us again. So it forms at the polar front where warm westerlies and cold polar easterlies meet. Okay, at the polar front, which is at 60 degrees. So of course, it also forms at the 60-degree latitude again in the northern hemisphere, right? Okay, so it does not only form in the southern hemisphere. So that's the area of development, and that's the only condition that is required for its development. Okay. You have to have cold polar MS from the cold polar easterlies and warm tropical air from the warm westerly winds meeting up. So that's the only thing that you need. Or you can say an imbalance in energy between different MSs, which of course are the subtropical westerlies and the polar easterlies. Okay, where friction will begin, frictional drag. We'll talk about all of that. Okay, but the most important thing is that subtropical westerlies meeting up with polar easterlies starts up the whole formation of mid-latitude cyclones. Okay, so that's where that's where everything begins. Right now, where, when, when when do these cyclones actually affect Southern Africa? So focusing on Southern Africa, and Southern Africa really um, forms somewhere over here. Okay, so this is Southern Africa over there. Okay, like that. So as you can see, because we're saying that it actually affects these areas right over there, and hence, of course, Southern Africa is mostly affected. Okay, indeed. And so, why is that so? Okay, why does it only affect Southern Africa? Okay, so exam question will be like that. So you should be able to answer that. Well, this is because, guys, and it only affects Southern Africa only in winter. Okay, only affects Southern Africa in winter. Okay, so let's think about this. Yeah, so you have this zone right here at the equator. So if you look at the equator, you can see that there's actually two tropical easterlies that are meeting up. They are converging. Remember, we said converging is meeting up. Okay, in the previous lesson. So they are meeting up there, okay, and they are where? They are in the tropics, this region between 0 and 30 north, 0 and 30 south is what we call the tropics. So that zone, this whole region, we call that the intertropical convergence zone. Okay, it's what we call the ITCZ. Okay, that's the ITCZ. It's the intertropical convergence zone. This is right here at 0 degrees. So the intertropical convergence zone is quite important when it comes to the migration of all weather systems, because when it moves, the weather systems follow it. Okay, and the ITCZ, guys, follows summer. Okay, I'll write it like that. So this follows summer. Okay, so that means that it will move toward um, a, a hemisphere that has or in which the season is summer. Okay, so if it is summer in the northern hemisphere, the ITCZ will actually move towards the north, right? If it is summer in the southern hemisphere, the ITCZ will move towards the south. So it actually follows the hemisphere, or it moves towards the hemisphere that has the summer season. So let's look at this now. So if we have summer, okay, let's do that. So if we have summer in the northern hemisphere, right? So what will happen? The ITCZ, okay, this ITCZ will actually move towards the north, right? to move towards the north because there's summer in the north, right? So if it's going to move towards the north, so that means that it's going to be situated slightly northwards, so maybe over there. Okay, so as it is moving towards the north, it is dragging along with it these mid-latitude cyclones. So if a mid-latitude cyclone was, let's say this is the southern hemisphere right here, the mid-latitude cyclone was over here, but because the ITCZ has shifted towards the north, the mid-latitude cyclones now, as you can see, were much more closer to the southern Africa, and hence it will affect southern Africa. Okay, so that's the concept around that. That's why it affects southern Africa over winter and not over summer, because over summer the ITCZ of course will move southwards, and hence the mid-latitude cyclone will also move southwards, and then of course southern Africa will not feel its wrath. So we're saying that the northern or the northward migration of ITCZ with it the migration of high pressure cells results in the low pressure systems moving over southern part of Africa. Okay, so that's what we are saying here. That's what you write down if they are asking you about why do mid-latitude cyclones affect southern Africa only over winter. Okay, so that's this is what you use to explain that, right? Sorry about that. Now let's look at some of the characteristics of mid-latitude cyclones before we actually enter and look at the stages of development. Okay, these are quite really interesting, but yeah, we'll get into that. So the characteristics is saying that we see a clockwise movement of air in mid-latitude cyclones where in summer, right? So we see this type of movement, this clockwise movement. I mean, in the southern hemisphere. I'm sorry about that. So we see a clockwise movement of air in mid-latitude cyclones in the southern hemisphere. So there's only clockwise movement of air, guys. So as a mid-latitude cyclone is moving, inside it, there's actually air that is actually rotating in a clockwise manner in the southern hemisphere. But of course, that's opposite in the northern hemisphere. There's a presence of a cold front. Okay, now cold front, guys, is simply this is like a boundary. Okay, remember a front is basically a boundary between different air masses with different densities. So a front, general front, could be maybe like there's warm air on this left hand side and there's cold air on this right hand side. So a front is it could be, so cold air could be on this side, warm air could be on this side. But when it comes to a cold front, now cold front has a front part and has of course a behind. Now cold front, this is how we draw a cold front. We use a line and it has these triangles. Okay, so these triangles actually point or show you that this is actually the front, actually like the front part of the front. I don't know if you get me there. So so for an example, a car, so you would definitely say that um, okay, this car really, let's say, yeah, the engine is right over here. Okay, and then the boot is right over here, and so of course the front part of the car is this. Okay, this is the front part of the car. Now these triangles show you that this is actually the front part of this front. Okay, and then behind this rectangle, these triangles, you have this is the behind part of the front. Okay, so now a cold front has cold air behind it. Okay, so that means that you only find cold air on this side. Okay, always that's a cold front. Okay, so I need you to note that. Okay, so we're saying that it has it has a presence of a cold front, so it has a cold front. It has a cold sector. Okay, we'll look at the cold sector, which is simply an area of cold air, which is behind the cold front. It has the presence of a warm front. Okay, so a warm front also, of course, is basically a boundary between two different MSs, but in this case, behind the warm front is warm air. Okay, so this is how you draw a warm front. You use these semicircles, and so this serve as the front part of the warm front. And so that means behind this, meaning which right over here on the left hand side, you should have the warm air, because behind a warm front there is warm air, behind a cold front there is cold air. So that's how it works, right? You also have this, that the mid-latitude cyclone is also made up of a warm sector, which is area of warm air. It moves from west to east because it is driven by stronger westerly winds. Very important, okay? This is very important. They like to ask this. So we're saying that uh, um, a mid-latitude cyclone will always move from west towards the east. So it's always looking to move towards the east, right? Why is it moving towards the east? Look at this region. Which the major winds that you have here, which are the subtropical westerlies, where they are moving towards. They are moving towards the east. So they are pushing this. So if you move into this region, just think of this as a fan, a huge fan. So it pushes everything, of course, towards the direction that it is moving toward to. Okay. So as you can see, if this mid-latitude cyclone forms here, okay, the polar front, then when it moves into this region, it will be forced to move towards the east. Okay, so that's what we're saying here, right? So it is actually forced to move from west to east due because it is driven, it is pushed by the subtropical westerlies, right? Simple as that, guys. It affects the western side of continents in the mid latitudes. Okay, so usually affects these areas right over here. So the western parts of continents in the southern hemisphere. Okay, so as you can see, it usually affects the western part of the because it is moving from west to east, right? These can be actually huge. That's why they are called extensive low pressure systems. Um, and the reason why they are also called extensive low pressure systems is that they actually do not cause as much damage, or they are not as intense as their brothers, which are your tropical cyclone. So the diameters can actually reach up to 3,000 kilometers. So between 1,500 to 3,000 kilometers. So that is huge compared to tropical cyclones. So they can be really huge weather systems, and they can travel at a speed of 50 to 60 kilometers per hour, okay, which is quite slower compared to tropical cyclones. They have a lifespan of system. They have a lifespan between 4 to 14 days, so it can last up to 2 weeks actually. The mid-latitude cyclones, right? They usually occur in families. Okay, so you can have more than one mid-latitude cyclone. Okay, so we said that mid-latitude cyclone again is made up of a cold front and a warm front. Okay, so this is how you draw it. This is our cold front. It's the front end of it. Of course, behind it should be cold air, and this is our warm front. Okay, the semicircles, and behind it, right over here, should be the warm air. And so this makes up one mid-latitude cyclone. So if you can actually have more than one actually traveling together like that. Okay, so they can travel together in that manner, right? So when they travel together in this manner, we then call them the a family of cyclones. So we say that they are a family of cyclones. Okay. So the one that is furthest to the east, okay, the one that is right over here, this should be, so if this is the southern part of the southern Africa, so this should be the oldest, right? It has already passed this southern Africa part, so it has already passed that because it is furthest to the east. That means it was the first to actually arrive. Okay, so if you move back in time, you actually realize that this one right over here was the first to affect southern Africa. Okay, so you should be able to spot these, and should be able to spot the number of these cyclones. So there's one, there's two, and there's three. So there's three mid-latitude cyclones right over here. Okay, and you should be able to spot the order of existence, guys. Okay, they like to test that. I'm sure you are aware of that. Okay, so with that we call them, when they're traveling together, we call them uh, a family of cyclones. Okay, call them a family of cyclones. Let me just write that down. Family of cyclones. Right. The next point, we say that it forms all year, but better developed in winter from April to October. So that is where it is actually affecting southern Africa. Okay. Now let's look at the stages of development. You can be given in your exams or your tests. You can just be given a diagram like that, and they can ask you which stage is it. So you should be able to identify each stage using the clues that I'm about to give you. Okay. So a mid-latitude cyclone develops in four stages. Okay. The last stage is actually its disintegration stage, or um, its ending stage. Okay, where it actually dissipates or ends. Okay, or loses power. Right. So of course, the first stage is what we call the initial stage. Where does this happen? Where do you think it happens? Of course, guys, it should happen right at 60 degrees, okay? Where you have these warm subtropical westerlies meeting up with these cold polar easterlies. So what happens is that, there we go. That is our 60 degree. I've just zoomed in there. That is our 60 degree. That means that is our polar front over there, right? So this starts the polar front. Um, so we say that you have these warm subtropical westerlies. Of course, they are moving from the west towards the east. So as you can see, guys, everything, these MSs are actually not interacting with each other. They are moving to opposite direction. This is our subtropical westerlies, and these are our cold polar easterlies. So this is cold air, and that is warm air, right? They are moving in opposite directions. Now, the polar front is still stationary. Okay, so we say that in the initial stage, the polar front is stationary. So this is one of the clues that you can use to identify that this is an initial stage. Look at the polar front, because the shape of the polar front actually changes throughout these stages. So in the initial stage, it's actually stationary or just horizontal or straight like that. Okay, so another thing that we see is that warm westerly winds and cold polar easterlies blow in opposite directions along the polar front. They are actually not interacting with each other, they're just blowing in opposite directions. Okay, and they do not mix. Okay, even though they have different densities, temperature, humidity, so on and so on. So as of course you have different MSs between each other, friction develops. Okay, we call it frictional drag. So these are moving at high speeds past each other, and so there's what we call frictional drag that develops. So frictional drag actually encourages these to actually move towards each other. Okay, but we don't see that yet. This is still the initial stage. So due to frictional drag, now you start to have warm air moving towards cold air. Okay, so now warm air will start to move towards cold air because of that friction that actually develops there. So it attracts warm air to cold air. Right. Now warm air, now another thing that you should know. So one clue you should note about the development stage is that you have this shape of the polar front, which is like a wave. Okay, so it is no longer stationary, it is no longer straight, it's no longer horizontal, but it has this shape. So as you can see, this shape that is like that. So that's when you would this is the only state that has in which the polar front has this type of shape. Okay, so as you can see, the polar front is no longer straight, it has it forms a wave. Okay, that's why we also call it a wave stage, right? Now a small mass of warm air, due to this frictional drag, this small mass now we want to move towards, okay, this is the top view, guys, so this will want to move towards the cold air. What did we say when you have warm air moving towards cold air? So you have this warm air, okay, say, so this looks like this, and warm air looks like that. They are moving in opposite directions. Now warm air wants to, or a small mass of warm air moves towards cold air. Now on the side, if you are looking at the side view of all of this, see that, okay, this is cold air, this is warm air moving towards cold air. And so what does it do? What happens when you have cold air and warm air, or warm air to moving towards cold air? It rises up, it is forced to rise up, or it is pushed upwards. Okay, and so hence an area of low pressure develops there. That's why we have this L there, guys, because warm air is actually rising up. So it's putting less pressure on the ground, and hence an area of low pressure develops. Okay, so that's why we see this low pressure, and you start to see that these isobars are actually dropping. So as you can see, the isobar value is now 1006 hectopascals. In the initial stage, it was moving from 1010 to 1008, like that, 1008, 1010, but now it's dropping. So you have more warm air rising up, more that the isobaric value actually decreases, right? So the rising air causes a low pressure in the center. So that is what is happening there. We don't see the cold front and warm front clearly because this is just a mixture of these. Okay, it's not, we cannot say that this is clearly a cold front because we also do see semicircles and triangles there. So cannot say that this is a cold front or a warm front. So they are starting to develop, and so this would indicate to you that this is still a development stage or a wave stage. Now let's take a look at the mature stage. So right from the start, we can already see that the the cold front and the warm front are clearly visible, guys. Okay, so they are well developed. That's a clue that this is indeed a mature stage. Okay, so this is a clue that you can use to identify that, okay, that this is a mature stage. Okay, sorry about that. So we're saying that as more air actually rises up, okay, so more air is rising up. So if you look at this, so more air is actually moving towards this cold air. So this is what is actually happening. So more air is actually moving towards this and is rising up towards you. As you are viewing this video, is moving towards you, that means it is rising up. So more air is rising up, more air is rising up. So of course this will this space right here, okay, or this area will eventually close up because more air is actually forced to rise up. And so um, this cold air actually closes up the space, will close up the space more and more, okay, as more air rises up until there's only cold air that is left on the ground. Okay, so now it's saying that the low pressure intensifies. Why would it intensify? Well, because more warm air is rising up. Okay, so that's why we say that the low pressure intensifies. So it's actually more air that is rising up at a high speed, okay, or at a higher rate. So it then moves into the westerly wind belt away from the polar front. So this is when, so at the mature stage, this is the stage where you see this. This is where we see that this is actually moving into this mid-latitude cyclone is moving into the 40 to 60 degree latitude at the mature stage. Okay, so it only moves into that region at the mature stage. Okay, so that's what you should know there. Okay, now a well-developed cold and warm sector develops. So these are sectors. So sectors, this is say that this area, right, only has warm air. So this area is what we call a warm sector. So this entire area right over here between the front of the cold front and the back of the warm front is what we call the warm sector. Okay, so I'll use color red, so it's called the warm sector. This is an area where there is warm air. Okay, this is the warm sector. And as you can see behind, guys, right over here, this is still behind the cold front. Okay, so this is still cold air, right? So we still have cold air here. This is all cold air, right? And this is all warm air right here inside. Okay, so this is what is happening. And so we then call this part where there's cold air, we call it the cold sector, right? Okay, cool. So cold, dense air moves faster and forces light, humid, warm air, less dense air in the warm sector to rise up. So as this cold front is moving, pushing this or forcing this warm air to actually rise up above it, so it is moving faster than this warm front, and so it is closing the space up. Okay, it is closing in on the warm front. Okay, so the cold sector becomes larger than the warm sector as the cold air moves and lifts up the warm front. So as you can imagine, this will end up you will end up having this very cold front right over here. So as you can see, the space is being reduced, and so that means that there's going to be more space of cold sector. Okay, so that's what we're saying there. It's closing in, guys, the cold front. So that's how you identify the mature stage. Look at the fronts. And then in the occluded stage, one thing I forgot to put in here. So this should be like that, yes. So in the occluded stage, as I said, the last stage, this is the last stage. This stage is where this actually loses power, the mid-latitude cyclone. This is the last stage of the mid-latitude cyclone. So because now you have more and more warm air rising up, the warm sector becomes narrow and narrow and narrow because, of course, the cold front is closing in, closing in, closing in. So as you can see, the warm sector becomes narrow and narrow. And hence, now that's why it is narrow here than over there, okay, and at the occluded front, at the occluded stage. Okay, so that's how you identify the occluded stage. But not only through that, but also you can look at this front. This front is what we call the occluded front. Okay, it's a mixture, a blend of these triangles and semicircles. Okay, so this is an occluded state. This is where the cold front actually overtakes the warm front. Okay, so cold air wedges in under the warm air. So what do we mean by that? Cold air moves under the warm air rises above like that. Okay, so the warm air becomes isolated from the ground because now eventually all warm air will rise up, and now you will end up having warm air in the upper atmosphere and cold air in the lower atmosphere. Okay, when you look at it from the side view. So now this is a stable condition. So cold air and warm air. Okay. Eventually all the warm air has risen up, and so yeah, this is the end of the mid-latitude cyclone. So this is what is called the occlusion. When how you define it is, say this is when the cold front overtakes the warm front. Okay, and all the warm air that was at the surface has actually risen up. Okay, that is what we call an occlusion. Okay, so this is it, guys. I hope you really benefited from this. In the next lesson, we should finish up, of course, by looking at the weather patterns that are associated, looking at the impact of mid-latitude cyclones, the weather changes that it brings, and of course, look at the cold front occlusion, warm front occlusion, the strategies, so on and so on. Okay, so that's what we're going to focus on, and I think we should do a separate video on activity. So we should do a couple of activities in one video. Let's make it one video. Do as many activities as we can on mid-latitude cyclones. Okay, so to test out our knowledge. Okay, so I hope you guys are having a great time, and I hope that this has benefited you a lot. I'll see you in the next video of our series. Bye.